We're looking for the math for the graphic design for the next ICM. There were tried many ideas, and I was personally very inspired by the work of Lisitsky with his three-dimensional object, curved object, a lot of interesting geometry. But what eventually was selected is more inspired by Kazimir Malevich and his very simple shapes, namely squares, solid colors. So it took me a while to warm up to these ideas, but then I realized there's some cool math about squares too, so I'm going to talk about one today. It's particularly about square tiling. So like, for example, here, here you can tile the whole plane with just two kinds of squares. So this is, maybe imagine these two squares, and if I just periodically repeat it, this is going to tile the whole plane. This is the simplest tiling you can make out of squares which are not all equal, and it illustrates something with the Pythagorean theorem. So the way it works is that, think about, so you can either, so you can take this figure and so maybe anchor it at this red dot, and so then we move it. You can anchor at all the other red dots here in this picture. But if you connect all these red dots, I'll try my best. And so then that should have been a square. I did it. So you can imagine it's a square. And so what this illustrates that you can either tile the plane with this two square or with this one square repeated. And so it has to be the case that the area of these two squares equals to the area of this big square. And so this is a really Pythagorean theorem, because to see this, you can think that this piece is the same as, so if you want to take these two squares and move it to inside the yellow square, then this piece will go here, that piece will go there, and maybe this piece will go over there. And so this illustrates that out of these pieces you can construct either one big square or two small squares, and that's the a squared plus b squared equals c squared. So that's a nice illustration.
And this overall tiling is the simplest tiling you can do, other than just squares?
Just other than just square grid, yeah, that's the simplest one.
Those two different sizes, is there anything interesting about their proportion to each other?
No, they can be arbitrary. Yeah. So this because in a squared plus b squared equals c squared, you can choose a and b arbitrary, right? So
and same with the tiling then, it could be a giant square and a small square?
Yeah, exactly. What changes in the video is that the size of the smaller square changes, and so all the tiling starts kind of waltzing around. There's something really neat math involved about how you generally think about square tilings, and so maybe I'll explain it here. So this is a tiling, so it's a piece of a tiling of a plane by squares. We're going to represent it like this. There's a lot of notation here. I'll explain it in steps. So what we see here are squares, and squares are numbered 1 through 15. So this is numbered in white. And then there are horizontal lines, and the horizontal lines, if several squares share the same horizontal line, I consider it as one horizontal line. I drew them in red, and I labeled them from the beginning of the alphabet. So this is A, then this is B, this line is C, and so forth up to down to H. And there are vertical lines, the same thing, but just if some squares share the same vertical line, I consider it as one line. And I labeled it from the end of the alphabet. So this line is Z, this is Y, this is X, W, V, and U. And so now we want to represent this picture as a graph. And what will be in the graph? Here, now you can make a choice. And the fact that you can make one choice or the other choice will be interesting later. But now we will choose to...
One quick question.
Yeah.
Where did this tiling come from? Like,
no, this is just I just imagined. You
just made up lines.
Exactly. I just made it up.
This wasn't a special thing.
No, just a random one. And so now we're gonna discuss how you think about tilings in general. And so in particular, you'll see how you can generate a random tiling or something more interesting than this. And so it's the graph in the plane. It's a bunch of vertices connected by a bunch of edges. And since it's in the plane, it also has these faces. So this is like a face here. And so what will be the vertices? The vertices will be the red lines. Actually, in New York City, A is blue. And it's also lined with subway, but anyway, this didn't work out. So the red lines will be the vertices. So this is A, and I put it at the same height as A here. But so then there's B, C, D, and so forth. And what are the edges? The edges is when the square, so say square 5, and it has a line at the top and a line at the bottom. So here the 5 is between A and C. And so 5 is this edge here that connects A to C. And so maybe this square 7, goes between C and F. And so here's this edge 7, C and F. So the vertices are the horizontal lines, the squares are the edges, and then the vertical lines, they are the faces, like look here. So there's a vertical line. It's surrounded by squares 7, 11, 8, and 12. So we look at this x here. 7 and 11, there are 7 and 11 here, and 8 and 12, they're on the other side of this vertical line. And now the most important thing, how do you remember the actual size and positions of the squares if you look at this graph?
By the way, everyone, I did try to get the professor to use brown paper, but he won a Fields Medal. He gets to do what he wants.
The main thing is that we have to record the actual shape of this picture, and we need to know what is the height, what is the horizontal, what's the height of each horizontal line. So there will be some equation so we need to know the height of each, like for example, the height of each C. It's just the vertical coordinate of this horizontal line. If we know this vertical coordinate, we know this whole picture. And what is the equation on this height? If we look at the length from here to here, it's on the one hand is the size of this square, of the square 4, plus the size of the square 5. And on the other hand, the size of the square 7 plus the size of the square 8. So the equation is the size of 4 plus the size 5. That is equal to the size of 7 plus the size of 8. But those sizes, what are they? So the size of the square 5 is the difference between the height of the line A and the height of the line C. So we get the height of A minus the height of C plus the same now for 5, so the height of B plus minus, this is what the brown paper is good.
That's all right.
Minus the height of C, and that is equal to the height of C minus the height of, so now this F plus the height of C minus the height of, so the other thing is D. And so when we rewrite this, we get the height of C is 1/4 of the height of the sum of heights of all its neighbors.
Where did that come from, Professor? Is that just fell out of that?
Rearranging this. This is just rearranging this equality. So the equality that what comes from the sizes of squares that come from the top add up to the same amount as the sizes of squares that come from the bottom. That becomes the equation that the height of this line is the average of the height of these 4 lines. Or if you look at this graph, the value of the function at this vertex is the average of the value of this function and all of its neighbors. So that is called, such a function is called harmonic. This is a very important notion in math. The result of this discussion is that a square tiling is a graph in the plane together with a harmonic function on this graph. A harmonic function is the one that the value of it at each vertex, like the value here, should be the average of the value of all of its neighbors. It's like if you think of maybe people think of some social analogy when the society, maybe there's a harmony in society if what a person has is the average of all the people he's connected with, and then maybe the society is in harmony. Or anyways, harmonic functions are very important in everything that has to do with 2 dimensions. So like any kind of mathematical physics that has to do with 2 dimensions, they're important in electromagnetism and fluid mechanics and in all they also so harmonic functions you can study in the discrete situation, like here. So it's like have a graph and something and a function on the vertices of the graph, or you can study in the continuum. So maybe in the continuum we'll do in the brown paper. Before we go there, there's a very important notion of which is illustrated in this picture. There's a very nice notion of if you have a graph in the plane, then there's a notion of a dual graph. And if you have a harmonic function, then there is a notion of a conjugate harmonic function. Maybe we'll explain with this picture. And so what is the dual graph? Here we made the choice. We decided the vertices of the graph are the horizontal lines, and edges are the squares, and the faces are the vertical lines. But of course, the picture is completely symmetric between the horizontal and the vertical. If I just look sideways, what was horizontal, that becomes vertical. And so in this picture, in terms of graph, that means the following duality for graphs. If you have a graph in the plane, then you can you can introduce a new graph called dual. The vertices of the dual graph are the faces of your original graph. That would be the vertex of the dual graph, and will be another vertex of the dual graph, and they're connected by an edge if these two faces were sharing an edge to begin with. Here's an example. So what was a face before becomes a vertex, what was an edge stays an edge, and what was a vertex now becomes a face. So this is, you see that this is going around the face. And if you had a harmonic function on a graph, then there's a related function on the dual graph called the conjugate harmonic, which in this case is just the, so this is again very simple to explain. Instead of recording the height of the horizontal lines, you record the x coordinates of the vertical lines. That will be your conjugate harmonic. So you say this is the edge number 7, so it's the one at here. And since this is a square, what we have here is that the change of the function, of the height function between these two vertices equal to the change of the height function between the dual vertices, because that was a square. And that's the general definition of a, well, maybe we'll do the rest on the brown paper.
So, Professor, if I got out a ruler and measured all the distances of everything here, like, you know, to the millimeter, you're saying, and I could feed them into these equations? And
that's exactly, that will be exactly the...
So, is basically what you've done here is you did a tiling, and then you've just shown me other ways to represent it.
Right, but it's in reality it's the other way. You can write an interesting graph, and then there'll be so then you can study harmonic functions on this graph. And harmonic functions on the graph, if you're trying to tile a whole plane, you can imagine that the very, very large distances, your graph may look something like a plane, and so your function will look like maybe some continuous harmonic function at the infinity. So this relates to the notions of continuous harmonic function, which I will discuss on the brown paper in a second. And so this is a fun combinatorial geometric way to think about harmonic functions. There's also a way to parameterize the square tilings by harmonic functions.
So do people who are trying to come up with tilings, because sometimes you'll see, someone's come up with a clever new tiling, are they using...
Yeah, of course, this is very classical. This is very classical. This was known to the mathematicians for the longest time. There's a lot of very serious mathematics goes into figure out how, if you study some discrete structure, such as a square tiling, or some other combinatorial or random structure which are discrete, and how on a very large distance, on a very large scale, they will behave as something we know from the continuum. From the harmonic functions were first introduced in the continuum, and they studied in like electrostatics. The electrostatic potential is an example of harmonic function. People studied it for what it is. It's very interesting how this large-scale continuous thing emerged from small scale discrete combinatorial things, and that is actually relates to some very concrete problems in mathematical physics, because one thing mathematical physics try to do is try to connect different scales. Like, for example, we know that solids or liquids, both of them are really discrete on microscopic scale. So there's something happens on the microscopic scale. At the large scale, we see equations of, say, elasticity or hydrodynamics or other equations of continuous mathematical physics. And it's a challenge, sometimes an easy, sometimes very hard one, for mathematicians to, starting from a microscopic description, justify the macroscopic behavior. And one thing which really helps, if you can somehow reduce your microscopic problem to a problem about, say, harmonic functions, because harmonic functions, they have a really nice, so if you have a harmonic functions on graphs, and the graph kind of approximates something continuous by becoming denser and denser, then you know the harmonic function, discrete one, will converge to a harmonic function, the continuous one. Now suppose you have a continuous harmonic function. And so we have a function of two variables, some function f of xy, and what's it called harmonic? What's the continuous analog of the property we discussed, that the value of the function at any point is actually the average of its value over all of its maybe some distance neighbors, or if you can in fact average over the disk. If I take the value at any point xy, this is equal to the average of f over this whole disk. That's the continuous version. And the basic property about harmonic functions in math is something you prove in complex analysis, that in fact they come in pairs. They come in pairs as the real and imaginary part of, in fact, a complex function. Like, for example, if I take the function of the form x plus I, which is I is the square root of minus 1, so this is the square root of minus 1, x plus iy, I square it, then by the law of algebra, so I'm going to get x squared minus y squared, this is the real part, plus this I times 2xy. And so now it's a theorem, not very easy to prove, that both of these things are harmonic, and moreover, they're conjugate in exactly the same sense as we discussed this with the graph. The level set of these functions, this is my function f, and this is my function g. And what are the level sets of z? The level sets of g, they're hyperbolous like that. So this is the level sets of g. This is where xy equals a constant. And what are the level sets of f? The level sets of f, they go exactly perpendicular. And so then if I look at the gradient is something which goes perpendicular to the level set, so maybe this is the gradient of g, and this is the gradient of f. They're exactly different, so this I messed up. This is supposed to be exactly the same size, and they're perpendicular. This is a continuous version of what we had here in the discrete. Here in the discrete, the two conjugate functions were the heights of the horizontal ones and the x-coordinate of the vertical ones. This function changes vertically by a certain amount, and the other function changes horizontally by exactly the same amount. So the gradients go exactly perpendicular. So that's a discrete version of that phenomenon over there.
Let's imagine a game with the following rules. We start with two numbers.
The sum of these numbers will be more than 50 trillion.
Great mathematical accomplishment, you really do things that you would not believe yourself are possible, and you have to find it within you.
No, I did not get it right.
How do you feel about that?
Well, you know, you win some, you lose some.
Did I make a big blunder? Turns out he did not realize.